Hi, my name is Jonathan Hoffman in the Microsystems Technology Office. My background is in atomic physics, and I came to DARPA with a real goal to try and take quantum sensing not only out of the lab and into deployed systems, but into the commercial market. The talk today is to talk about how we can impact and change quantum sensing for positioning, navigation, timing, and communications to revolutionize not just the DoD, but the commercial market as well. To get started, we need to think about what quantum sensing is and look a little bit at the history. And while quantum sensing may seem like a nascent field, it actually has been around for a while. And there's a dirty little secret, which is it's already changed the world. Starting on the left, in terms of medical imaging, magnetic resonance imaging, or MRI, has greatly impacted our diagnostic ability to locate diagnostically relevant issues inside the body non-invasively. This has changed medicine as we know it over the last few decades. In terms of sensing and communicating, I would claim that the laser is a quantum device, although now it's accepted all over the world and you have them in your pocket when you have a laser pointer. But it revolutionized communications. Our data centers, even the way we receive the internet today is over optical fibers. And in terms of navigation and timing, the global positioning system is foundationally built off atomic clocks that pass timing, which allow us to navigate. And this has impacted markets in ways that were unforeseen at the time for a system that was built for military use. Financial markets utilize it, data centers utilize it, even farmers today rely on GPS, and it's impacted the world in multiple ways. But this is just the beginning. And that's sort of long history, decades and decades old technologies. In the more recent future, we've built magnetometers that can non-invasively and at a distance measure active signals from the body, your heartbeat, your brain signal, your spinal cord, or even your gut. And how this can impact health in the future is an open question. And what the technological developments required to improve these sensors is also an open question. In terms of sensing and communicating, we have new quantum sensors based on Rydberg atoms that break what we treat as the traditional trade space between classical antennas, where typically we think that the antenna's gain bandwidth product is tied to the size and shape of the antenna relative to its operating wavelength. Here, using Rydberg atoms, we break that and don't have those confines, and we can detect anywhere from DC to a terahertz using these specialized states of the atoms. And in terms of navigation and timing, we've built incredibly precise clocks using optical transitions rather than the older microwave transitions that have been used for decades that are more precise and can be more accurate. And now we've actually deployed them at sea for weeks at a time without requiring intervention from a person. All of these things are great innovations, and I truly believe they are just the start of the quantum sensing revolution. But there are still a number of challenges out there to make these devices break into a commercial market. And one of them, those challenges I'll detail a little bit on this slide quantitatively. The issue is that today, many of these devices, which are quite spectacular and will be useful in the near future, are kind of like bespoke Swiss watches. They are hand-assembled. It takes an incredible amount of time and labor to build them. And so these devices aren't quite manufacturable as we would like. And that goes down to the inherent design space that has been utilized. So on this plot, we look at, on the y-axis, the relative performance. Up is better. And on the x-axis, the manufacturability. To the right is better. And our goal is to be up and to the right in that green corner for manufacturable quantum sensors. On the bottom right, we see scalable sensors, MEMS, microelectronic sensors, where we have an amazing market, and you've got devices in your pocket, in your cell phone, in your watches that can measure and give you relevant information. We produce billions of them a year. And their performance is good enough. They do the job, and they're quite spectacular. But if we go to the upper left corner, we have devices that are on the lab scale that have spectacular sensitivity and performance. Quantum sensors have made the most precise measurements of time, frequency, and field that exist. But taking them out of the lab has been a challenge. And when we do that, we try and miniaturize the lab scale brethren and go down into the right, into this region of those bespoke commercial quantum sensors. And that's because we're taking these lab scale designs and we're giving away the modularity and the freedom that the lab scale has in isolating various noise sources away to put them into a box. And when we do that, we sacrifice performance. And in fact, it's a little worse than that, where optimization in a lab isn't necessarily the optimization that you would utilize when you're trying to make a commercial or deployable device. In the lab, I have the freedom to isolate magnetic fields or electric fields that are stray, create no gradients, and isolate from vibration or temperature concerns. In the real world, that's not an option. So the question I'd like to pose to you is, how do we re-envision quantum sensors for manufacturability and for proliferation? How do we do that so we can move up and to the right in this chart and really develop the capabilities around the world that have the great performance, but now can be in everyone's pocket? Here's a motivational cartoon. This was done by this is an artist's concept for future manufacturable quantum assembly. And the idea here is to get you thinking. Of course, this isn't exact, this is not real, but to get you thinking about how can we leverage some of these wonderful tools that have come together in 3D heterogeneous integration of microelectronics, the elements that ERI 2.0 and NGMM are pushing on, as well as these major advancements in integrated photonics, to think about building building wafer scale quantum sensors, building all of these components together to building these components together to develop capabilities that would not even be possible on a benchtop, but then would be immune to environmental issues and potentially mass manufacturable at the wafer scale. Switching topics a little bit, quantum sensing has promised even better sensitivity bandwidth products than have been demonstrated. So we normally think about them operating at devices operating at the standard quantum limit, which would be the atom shot noise, for example, or spin projection noise limit. And we've got examples today of atomic magnetometers and Rydberg electrometers that operate well in their different bands. But one question I would like to ask is, how do we develop methods that improve the sensitivity bandwidth product beyond the standard quantum limit? How can we really utilize entanglement as a resource and push on this sensitivity bandwidth product for communications markets? If we can build this, we can envision a future where every cell phone has a quantum sensor in it that's picking up all of your 5G, 6G, 7G plus reception. So how do we enable quantum sensing that could dominate the communications market? And one way that I think is very exciting is beyond standard quantum limited sensitivity bandwidth products. So with that, I'd like to end by saying we need your help. We need your help figuring out how we can push this technology forward. How do we proliferate quantum sensors? What is that going to take in terms of redesigns on a fundamental level? What's necessary for these devices to create entirely new markets, not just taking over existent markets? And what modalities exist for devices beyond the standard quantum limit? I'd be very excited to chat with any and all of you. Please do not hesitate to reach out, and I really thank you for your time.